Now today I want to go through a couple of laws in astrophysics, the first one being Wien's law. And this is a law for black bodies. You don't need to know too much about black bodies except that when we categorize a star as a black body, we're assuming that is a perfect emitter and a perfect absorber. Now every star emits a different amount of each wavelength, and he found out that the amount of each wavelength that they emit is dependent on the temperature. So let's say this star had some random temperature value of, let's say, 8,000 Kelvin. We're going to call this value here lambda max, and lambda max is where there is most emission of that wavelength. The intensity at that specific wavelength for that star is maximum. So that's this lambda max value. He figured out that stars with different temperatures have different spectrums. So let's say a cooler star would have a spectrum like this. So this star could say have a temperature of 5,000 Kelvin. And the lambda max value for this star is there. And then let's say we had an even cooler star that looked something like that. The lambda max value would be there. And the reason I've called these values lambda max is that he's found out a relationship between temperature and this lambda max value. And that is lambda max times by the temperature in Kelvin is equal to 2.9 times 10 to the minus 3, and the units of this 2.9 times 10 to the minus 3 is meters Kelvin. So if you were to get a spectrum for this graph and you were to able to identify the lambda max value of this star, you could therefore work out the temperature of that star. And for those who do chemistry, this graph here is very similar to that of a Boltzmann distribution. Now this next law is called Stefan's law. Now Stefan's law says that the power is basically the luminosity, or how much energy radiation this star is emitting. He found out that this power, or this luminosity, is directly proportional to the temperature of that star to the power of 4. And he also found out that the power of the star is directly proportional to the surface area of that star. So they came up with an equation that is P is equal to sigma A times T to the 4. T being your power or your luminosity. So sometimes this is denoted by a letter L. A is your surface area, that is 4 pi r squared, where r is your radius of the star, T is the temperature in Kelvin, and sigma is your Stefan's constant. And Stefan's constant has a value of 5.76 times 10 to the minus 8. And you can find that both in your data booklet and on your calculator. Now this here I've taken from the AQA website. This is a spectral class table for different stars. And it shows that different stars are categorized into different classes based on their temperature and certain other things. And these classes are labeled O, B, A, F, G, K, M in order of decreasing temperature. And you can also see that they have different colors and different, some of these called prominent absorption lines. Now it's very important that you remember this table off by heart. You will not be given this in your exam. The main things to remember are what is the color of each spectral class and the temperature. Those are the two most important things, but you definitely should remember the prominent absorption lines as well. The best way to remember this is to just keep looking at it and keep repeating the colors and repeating values for the temperatures, and it will get stuck in your head. Now this here is something called a Hertsprung-Russel diagram, or a HR diagram. Now on the y-axis you can see that we have absolute magnitude, and on the x-axis I put spectral classes. But if you look back at the table, you can see that spectral classes are only really dependent on temperature, so you could equally have temperature on this x-axis. But just be careful that on the left I've got a larger temperature and on the right I've got lower temperatures. This graph shows where different stars are placed. This big line in the middle is the main sequence stars. So any main sequence stars will be found on this region there. At the top right, we can see giant stars, such as our red giants, and you can even find stars up here that are known as blue giants. And in the bottom left, you can see that we have our white dwarfs. Now, our sun is in a spectral class of around G or K, so our sun is probably there in our main sequence. And main sequence stars are ones where hydrogen fusion is occurring. Now, these red supergiants are very, very up here, and they're on the right hand side because as these stars expand, their surface temperature will decrease. And as we know, if something's bunched up, it's going to be hotter, but as it expands, it gets a lot cooler. But the reason why it's got such a great absolute magnitude is that it has a very large surface area. And remember that we know that power is directly proportional to the area, so a larger area means greater power, which therefore means a greater absolute magnitude. Now, white dwarfs have very low absolute magnitude, and this is because they are very small, but they have a high surface temperature, and that is why they are in the left hand side of that graph. You can see there that they're in the high temperature section of the graph. Now, the best piece of advice I can give you after watching that video is to go off and practice some past papers or topic questions. These are single-handedly the best way to help you commit the content you've learned to memory. Obviously, go and do all the YouTube stuff of liking, subscribing, and if you found this video helpful, feel free to go and watch any of my other ones.